Travan's sister, A. John Diana, Vice Principal, to this session. Welcome you, sister. Most people think of success in terms of getting success, however, begins in terms of giving. So, now I invite the resource person, Dr. R. Lakshmipati, Assistant Professor, KCG College of Technology in Chennai. He has completed undergraduate in Sri Venkateswara University in Andhra Pradesh and Master of Science in Hoorhis College and PhD in VIT University. Totally, he has published 36 paper publications, 574 citations, and also many books and journals. He has he has 6 years of experience in VIT University and he currently working in KCG College Chennai. He is the convener of IIC under the aegis of MHRD Innovation Cell. He is also organized many training
just due to the air pollution and water pollution. So there is some serious problem that we need to deal with. So because not everyone has access to quality water. Now you can see canned waters are quite popular, right? Everyone we depend on canned waters for the drinking water, right? We don't use the tap water or the well water or borewell water because the borewell waters are salty and tap waters contain the nitrates and other contaminants. So we don't have access to quality water. So that is the problem with the water that we have. If you just go back to 15, 20 years back, we used to have access to some quality waters, and the bore water was quite sweeter and it's not so salty. And the well waters were also of good quality. But now, over a period of time, what has happened is because of the industrial activities and other man-made activities, the pollutant are easily getting mixed up with the water because the effluents that are coming out of industries are let into the rivers and lakes and the water streams. So as a result of that, what has happened is the water got polluted, and now we don't have quality water. So means people don't have access to quality water. So that's the reason why we are depending on the water cans and the RO units or the potable RO units that we have at our home for the quality water. Okay. So there is one bigger problem that we have in front of us. That is access to quality water, because water is essential for our life, and this ecosystem will sustain with water. Without water, this ecosystem will not sustain. Right. So what is an important or essential part of our life? So now we'll just discuss about how adsorbance plays an important role in converting wastewater or polluted water into a potable water or drinkable water. So we're going to discuss about that. Before we just discuss about the role of adsorbance, I'll just take you through what is surface chemistry, because there's a direct link between the adsorbance and the surface chemistry. Okay. So first we need to understand what is the surface chemistry, because this is the thing that happens behind any adsorbent. Okay. Means there is an interaction that is taking place. Okay. So surface chemistry is nothing but it's a phenomenon where we study about the surfaces and the interactions that takes place between the surface and the other molecule or whatever it might be. So the interaction between the surface and the chemicals. So what type of interactions are taking place? So study of that is what we call it as surface chemistry, or surface chemistry deals with the surface interactions. So if you see surface chemistry is not happening somewhere else. Okay, so you see it is happening in every day-to-day life. No, every day we come across surface interactions. Okay. So it is very much applicable in industries and even in our day-to-day life. Every day, different surface reactions or surface phenomena are taking place, and we are coming across that, but we don't realize that this is a surface phenomenon that we are dealing with. Okay. So if you see, just here is a pictorial view, like what happens when a molecule or chemical compound comes in contact with the surface. Okay. Now, surface in the sense what? It is, say for example, it's a floor. So the floor itself is made up of some chemicals, right? So if you see, this universe is built up of built on atoms, okay, atoms, molecules, and compounds. So everything is, we can define that in chemical reactions or chemical formula. So the molecules are interacting with the surface. Now, how they are interacting? So study of that is what we call it as surface chemistry. Okay. So surface chemistry deals with the interactions that take place or absorb, whatever it is. Okay. So now there are a few terminologies that are associated with surface chemistry. One is adsorption, and second one is desorption, third one is absorption, and sorption. So we have different terminologies. Now I'll just quickly take you through these four terminologies before we discuss in detail about the adsorption. So what is adsorption? So adsorption is nothing but it's an sticking of molecules, that is the addition of atoms or ions or molecules, okay, onto the surface. So generally surface will be a solid one. So the interaction of molecules or atoms or ions, okay, it can be in the form of a gaseous state or it can be the liquid phase. It can be a gaseous phase or liquid phase. Okay. So when these molecules or atoms or ions comes in contact with the solid surface, okay, now what happens is they create a film, means they just stick onto the surface. They just stick onto the surface and it creates a film of adsorbate. Okay. So adsorption is nothing but just the addition of atoms or molecules onto the surface. So here you can see, here you can see there's a surface and where the water molecules are interacting. So we are just sticking onto the surface. Now when we add water onto the floor, okay, or onto let's say plate, so when you add some amount of water, okay, so you can see some water will be sticking onto the surface, right? So now what is happening there? Actually, it's adsorption. The water molecules will be sticking onto the surface. Yes, there is an interaction that is taking place between the surface and the water molecules. Okay. So That is what we call as adsorption. And what is desorption? So the opposite to that of adsorption is what we call it as desorption. That is removing the molecules or atoms or ions, okay, that got stuck onto the surface. That's what we call it as a desorption. It is the opposite to that of the adsorption process. Adsorption is what? Sticking of the molecules onto the surface. Desorption is removing the molecules from the surface. Is what we call it as a desorption. So here you can see molecules will be sticking on the surface, and that is what we call it as adsorption. And when desorption takes place, what happens is the molecules from the surface, now you can see here, the molecules from the surface, they slowly move away from the surface. So that's what we call it as desorption. So adsorption is sticking of the molecules onto the surface. Desorption is removal of the molecules from the surface. Okay, so that's the difference between adsorption and desorption. Okay, now we have another term which we call as absorption. Okay. So sometimes some people get confused with the terms adsorption and absorption. So absorption, AB, absorption is nothing but it's a bulk phenomenon. It's a bulk phenomenon where the molecules or atoms or ions enters the bulk phase. Means they don't stick onto the surface. Instead, they go inside the uh, material. Okay, it can be a solid material or it can be a liquid material, whatever it is. So they go inside the bulk phase. So absorption is a bulk phenomenon. So it's not a surface. Uh, they are not sticking on the surface. They are going inside the molecule. So that's what we call as absorption. Okay, absorption of light. Light goes inside. Okay, absorption of light. Okay. So there's a difference between an adsorption and absorption. Okay, but usually people get confused with the terms and ab because just only a letter is the difference between the adsorption and absorption. Okay. So now we have a term called as sorption. So this is a general term. So when adsorption and absorption both are taking place at one step. Okay, so when these two processes are taking place simultaneously, we just simply name it as a sorption instead of defining it as adsorption or absorption. Okay, we just simply term it as sorption, which means both the adsorption and absorption, two processes are happening. So there are a few more terminologies that are part of this adsorption. One is adsorbate. So the molecules which will be sticking onto the surface is what we call as adsorbate. Okay, the molecules are ions, whether it is in the gaseous phase or liquid phase, that we call it as adsorbate. And adsorbent is the surface, the layer. The surface material will be called as adsorbent, and the molecules or ions that are present in the liquid phase or the gaseous phase, we call that as adsorbate. Okay. So these are the few terminologies that I wanted to share with you before we discuss about the role of adsorbance. Okay, now what is the difference between absorption and adsorption? So here is a pictorial view, the difference between absorption and adsorption. You can see absorption, it goes inside. So this is the boundary layer, and the molecules or ions or atoms, okay, from the liquid phase or gaseous phase. Okay. So they are entering into the bulk phase. You can see these. Let us consider this black line as the boundary layer, that is the surface layer. So these ions are going inside. But if you see the adsorption, they're not going inside. So they are just sticking onto the surface. So as a result, they will be creating a thin or thick layer of coating. So a coating of the ions or the atoms or molecules can take place on the surface. So that's what we call as adsorption. And a real life example, I'll just show you a real life example. Okay. So if you eat something, okay, a piece of cake or a piece of pizza, whatever it is, okay, if we eat, then it's absorbing, means it's going inside, right? And instead of eating the piece of cake or pizza, okay, we have a birthday celebration. Now, what is happening? The birthday celebrations, people don't eat cake inside, no, they play with the cake and they try to apply the cake onto the birthday boy or girl. Okay. So that is sticking onto the surface, right? So that is adsorption. So absorption means something that goes inside. Adsorption is just sticking onto the surface. So this is the difference between the absorption and the adsorption. So I hope it is clear, I guess. Now, what are the applications of adsorption? Okay, so we are going to focus more on the adsorption rather than absorption, because adsorption has very wide applications in industry as well as in our day-to-day life. So What are the applications of adsorption? So applications, if you see, there are a number of applications, but I have picked a few important applications which we can easily understand and we can easily correlate with our day-to-day life. So one is vacuum flask. So now we know vacuum flasks are used to preserve the temperature of the solution what we use, right, whether it is cold or hot. Okay. And the flask and the outer body, the inner wall and then the outer wall, contains vacuum. Means in between we have vacuum. So why do we create vacuums? Because in order to preserve the temperature, in order to avoid the loss of heat or the loss of gain of heat. Say for example, we add hot coffee or hot water to this flask. Okay. Now it's going to preserve the hotness of the water, right, for a long period of time. Some flask will work for 24 hours, means it will preserve the temperature or it will retain the temperature. Okay. Why is? Because there is no medium for heat exchange. Because there is a vacuum between the inner wall and the outer wall of the flask. So there is a vacuum. Now this vacuum doesn't have any air, right? So if there is any air molecules or gas molecules that are present, so these gas molecules can absorb the heat and then it can transfer the heat to the outer, that is to the environment or to the surroundings. Now when we don't have air particles or atmospheric gas that is present inside, so when there is a vacuum, now there is no medium for heat exchange. So as a result of that, what happens is the temperature is retained inside the flask. Now, how
Excuse me, sir. Sir,
adsorption or
hello.
how adsorbance play a role? Now,
Excuse
uh,
me, sir. Hello.
yes,
Sir, the slide is not sharing, sir. It's not changed.
okay, you're not able to see the slide.
Okay. I can able to see, sir, but the slide is not changing, sir. I think it's first slide,
Okay,
I
which
think.
slide you are able to see?
I'm just seeing the first slide only, sir. The role of observance in wastewater treatment.
Okay, okay, give me a second. Give me a second. You could have
Yes, sir.
informed me earlier itself.
I'm sorry, sir. Sorry. Thank you, sir. Thank you.
Now, now is it visible?
Yes, sir. Yes. Thank you, sir. Thank you.
Can you see the full screen or
Yes, sir. Yes.
you can see the full screen, right?
Yes, sir. It's in full screen.
Okay. Okay. So if you see the applications of adsorption, there are many applications of adsorption. Uh, can you see the full screen? Because I don't see my slides being for the slideshow.
Yes, sir. It's shown. It shows the full screen.
Okay,
Your,
can you see the applications of adsorption then?
yes, sir. Yes.
You see the flask, right? The flask and then the content for the flask.
Yes, sir.
Okay, okay, thank you. Is there any change in that?
It's changing, sir. You're showing, I think, application of absorption, right, sir?
Yes, yes. No,
Yes,
there
sir.
will be so many pictures and then content, but if you can able to see this full screen,
Yes,
yeah.
sir. Yes, sir. In, I think, in preserving vacuum.
Yes, yes, yes. Yeah, that's fine.
Oh,
Okay.
okay, sir.
So in the flask, no, if you see, if there is any defects in the flask manufacturing, now gas can enter into the vacuum space. Now, when we can able to add some adsorbents like the activated charcoal, so this charcoal has the ability to absorb the atmospheric gases. So as a result of that, now what happens is we can able to solve the defects that got developed due to the manufacturing process or whatever it is. Okay. So this charcoal is going to absorb the gases that enters into the vacuum space. So the lifetime of the flask increases. So that is the one application of adsorption. And second one is the gas mask. So now we use mask, right? Because now because of this pandemic, we use mask, and we have a huge problem with the virus. And why do we use mask? Because we want to get rid of this COVID virus. Now this mask itself acts as an absorber. Okay, it acts as a boundary layer, it acts as a surface. So it just filters the bigger particles and just allows only the atmospheric gases to pass through the mask. So we can able to avoid uh, coming in contact with the COVID virus, and that's fine. But we have industrial gas masks, toxic gases. So they, in simple mask, cannot help us to come in contact or avoid inhaling these gases. So there we need industrial mask. So in the industrial gas mask, now we have activated carbon present. Okay. So that activated carbon will absorb all the toxic gases, and it allows only the nitrogen and oxygen. So that we another application of adsorption. And paint. In the paint industry, we use adsorbents, catalysis. So we know catalysis is nothing but using a catalyst. So usually we use a metal catalyst, right? Metal as a catalyst. Now these metal catalysts now will act as a surface. So where the reactants will come and get absorbed onto the surface, and then they get reacted. So first step is adsorption is what taking place in case of catalysis. So we have a theory called as contact theory. So it clearly explains like how the mechanism of converting the reactant into product takes place in presence of a catalyst. So the first step is adsorption. Reactants will get absorbed onto the surface, and then they react, and then they get converted into product, and then they get dissolved. Finally, they get move away from the surface. So in catalysis also we have applications for adsorption. And in chromatography, so you would have studied about chromatography. So even in chromatography, what happens is we take a column and then we just add the adsorbent and then the molecules or the mixture of compounds, and then we try to separate it with the help of a solvent. So again, if you see here, the adsorbent acts as a stationary phase. The silica, usually we use a silica gel. So that is being used as the adsorbent. That acts as an adsorbent. And another important application is now we know because of this COVID, okay, in the second wave, we have seen a huge amount of demand for the oxygen, right? So people were purchasing oxygen concentrators. So if you see here again, adsorption plays a role in the oxygen concentrators as well. So inside this oxygen concentrator, no, we have an adsorbent. There is zeolites. There is nothing but sand. So we have a specific zeolite, so which absorbs the nitrogen gas, and it allows only the oxygen gas to pass through. So we know atmospheric gas composition, right? 78% is nitrogen and 21% is oxygen. And the remaining trace amount of other gases will be there. So when we can able to separate nitrogen, okay, from the atmospheric gases, then we have only 22% of gases, and out of 22%, 21% is oxygen. Okay. So zeolites is a type of sand, okay, so has the ability to absorb the nitrogen gas. So as a result of that, we can concentrate oxygen and then we can supply it. So this is a life-saving device that has helped several people to get rid of this COVID, right? So oxygen concentrators, adsorption is the theory or the mechanism that is taking place behind this oxygen concentrators as well. Okay. So these are the few applications of adsorption. So now I would like to come to the main topic of our webinar. So that is the adsorbance for water treatment. So we initially discussed like we don't have access to quality water, and we always have access to polluted water, right? So there are several techniques which are in practice for converting the wastewater into potable water. But adsorption and adsorbents have an upper hand in converting the polluted water into potable water. Why is because the adsorbents are highly efficient, and they are eco-friendly, environmentally friendly, and few of the adsorbents are cost effective. Cost effective in the sense they are very cheaply available. So we can make use of that. Okay. So the first adsorbent that was actually tested or investigated for wastewater treatment is the activated carbon. So activated carbon or activated charcoal or activated carbon. So this particular material is a very good adsorbent. So which has uh, ability to absorb all the pollutants that are present in the water. So it can convert the wastewater into a clean mode. So that is the power of activated carbon. And even if you see the RO units, what we use at our home for producing the potable drinking water, even that has activated carbon chamber. So the water will pass through the activated carbon chamber, and then it will go onto the reverse osmosis membrane, and then UV filtration, everything, UV process, and then it comes out to the collection tank. So active carbon, still we are using the active carbon, but there's a problem with active carbon that once it is used, again the regeneration is the biggest issue that we are facing. Means any material that we use now, it should have ability to get regenerated. Means we should use that for 3 times or 4 times or repeated cycles. Like it's not like a one-time use. We should have several usages. So the problem with active carbons, once it absorbs the pollutants, so regeneration has become a problem. And production of activated carbon, again, it's a costliest affair because we need to take the material to a temperature of 750 degrees Celsius and above. So only in that case, what happens is the activated carbon can be produced. So taking to that temperature, we need a device and we need energy. So producing active carbon itself is a costliest affair. And after producing that, if you can able to use only for one time, then the limitations are there, right? So the applicability is going to come down. Right? So because of that, researchers are always in search of better adsorbents and low cost economical adsorbents, and which can be used for several times. It's not like one time, for several times we can able to use it. So likewise, what has happened is people have investigated a variety of adsorbents like agro waste, agricultural waste. So there are a variety of agricultural waste that are being produced. And every day now, if you see, we are discarding huge amount of agro waste. Now these agro waste are capable of actually or absorbing the pollutants. When they come in contact with the pollutants, no, they have the ability to absorb, like a rice husk and fruit peels, like banana peel, orange peel, and any fruit peel has the ability to absorb the pollutants. And the peanut shells, vegetable waste, any vegetable waste, waste materials that can be used, and coconut coir and the sugarcane baggage. So waste materials that are produced after processing. So if you see the fruit peels and all, we don't consume fruit peels, right? We just take up the edible part, and the fruit peels are discarded as a waste. So that peels can be used. And you can imagine the mango peels and then the other banana peels and all, how much quantity of mango peels are produced. Krishnagiri is famous for the mango pulp industries, and people you would have seen discarding huge amount of mango peels and then the seeds roadside and all. You would have seen huge amount of waste being discarded, right? So now these materials have the ability to absorb the pollutants. So if you can able to process that properly, and if you can able to convert that into an absorbent, we can use that effectively in converting the wastewater or polluted water into potable water. Okay. So now I'll just take you through what we do and what our research group has done till they like producing or fabricating the adsorbents and using the adsorbents in controlling the pollutants or treating the wastewaters. So what we have done is watermelon. We know this is a delicious fruit, right? Everyone likes watermelon because it is so attractive and so tasty. Now, if you see, the red part is edible one. So we just consume the red part and we just discard this white and then the green part, the rind. We call it as the rind, right? Okay. So we just discard the white part and the green part and we just consume the red part because the red part is so sweet and delicious. So we try to consume that. But the white part is not so tasty, so we don't consume that. And the rind, it's a hard one, so we don't consume that. So we discard it. Okay. Now during the summertime, you can see huge amount of watermelons are available or sold on the markets, and a huge amount of waste is also produced. If you just visit to a local fruit shop, you will see how much amount of waste is being produced. Okay, so the quantity is very high. So what we have done is we have converted or we have considered this outer ring, that's the green part and white part. We have collected that and we have converted that into an absorbent. So I'll just show you how we actually converted the watermelon ring into a adsorbent form. Okay. So we have considered the watermelon ring. So this is, we have collected these materials, okay, the green part and white part. We have collected that, and then we have washed it with tap water for several times in order to remove the dirt particles or any contaminants or impurities. So just to remove the dust and dirt, we have washed it with the tap water for several times, and then it was dried in the sunlight for 7 days. So in order to remove the moisture, because the watermelon, if you see, it contains huge amount of water. So in order to remove the moisture, no, so we have dried it under the sun for 7 days, and after that we dried bigger pieces, no, were made into powder. So with the help of a mixer grinder, a conventional mixer, we have converted that into fine powder. Okay. And then we have sieved it not to get a fine powder, because when we convert that into powder, you'll not be getting an even sized particles. We'll have smaller particles, we'll have bigger particles. Okay. So in order to have an even particle size, no, we have sealed it with a BSS 100 mesh seal. So finally, if you see, this is the product we have obtained from this green part. So after this, all these steps, finally we have a powder, so which can be used as an adsorbent. So now we have characterized this material, the solid material, the powder which we have obtained from the watermelon ring. So we have characterized with this various analytical techniques. So if you see, we have first considered this FTIR, that is Fourier transform infrared spectroscopy. So this FTIR is very much helpful in identifying the functional groups. So what type of functional groups we have. So FTIR can help us in understanding the function. So we have taken a powder and then we have analyzed the FTIR. So we can see here there are different peaks, right? So each peak represents a type of functional group. Functional groups like OH, hydroxyl group, functional groups like CO, C double bond O, carbonyl groups, and then C bond H, methyl groups. So FTIR helps us to identify the different types of functional groups that are present in the any sample, any compound. Okay. So we have used this technique in order to identify the surface functional groups that are present in the watermelon ring, because this can help us to understand the mechanism, like how the surface is interacting with the pollutants. That is, the surface chemistry can be understood with the help of this. So that's the reason why we have analyzed this material, the watermelon ring, with the FTIR. So we found it contains hydroxyl groups, it contains a carbonyl group, it contains acidic groups, carbonic groups, and then the methyl groups, and different types of functional groups are present in it. Okay, so we have confirmed that yes, it contains a hydroxyl and then carbonyl groups. So hydroxyl groups are very much helpful in binding the pollutants. So we have understood this. Then we have analyzed with the scanning electron microscope just to see the surface, how the surface looks like. It's a powder, right? So we have taken that to the scanning electron microscope, and it was zoomed at 20 micrometers. The sample was scanned, or this image was taken at 20 micrometers. So you can see how the surface looks like. It's a powder, but when we zoom it with the scanning electron microscope at 20 micrometers, no, you can see the surface looks like this. But it is little porous in nature. The material, it indicates that it's a porous in nature. And further, what we have done is, if you see with the FTIR, we can able to know what type of function groups are present in it. But we do not know what type of inorganic ions or elements are present in the watermelon ring, right? So for that, we have considered this energy dispersive X-ray analysis. In short form, we call it as EDX. So we have considered this energy dispersive X-ray analysis. So when the watermelon ring powder was subjected to this EDX analysis, we can see here different peaks. So it contains carbon, it contains oxygen, yes, because even in FTIR we have seen different functional groups. So that's fine. But apart from this CMO, Okay, now you can see here the magnesium, chlorine, and potassium peaks, right? So you can see the intensity of potassium. Watermelon contains huge amount of potassium. Okay. So when we consume watermelon, no, means we are consuming a potassium. Okay. So which is very much essential for our day-to-day functions. So that's the reason why people advise to take fruits, because fruits contain huge amount of sodium and potassium. Okay, so which acts as uh, electrolytes in our body. Okay, so that is really helpful for our day-to-day functions. Okay, so it actually fulfills the nutrients that are required, the essential nutrients that are required. So we understood that the watermelon rim contains potassium. The outer part contains a huge amount of potassium. Even the red part also contains potassium, and the white part and green part also contains the potassium. Okay. And it also contains chloride, and some quantity of magnesium is also present in it. Okay, even magnesium is also very important for us, right? Okay. So we understood that the watermelon powder contains the potassium and magnesium. Okay. So now all these understandings, like the FTR, helps us to understand the type of functional groups, and a scanning electron microscope helps us to understand the surface morphology, so how the surface looks like, and the EDX helps us to understand about the elements, the different types of elements that are present in it. Now, altogether, no, it can help us to understand how the mechanism takes place between the surface, that is the bottom land grain, and the pollutants. So what we have done after this is we have concept for the application one. So we have taken this watermelon grain in order to treat the water which contains heavy metal ions like the cadmium, nickel, cobalt, and chromium ions. And we have tested with the heavy metals, like how this watermelon ring can effectively control or effectively take up these pollutants or these heavy metals from the water. So we have, in fact, carried out several studies, and we understood that watermelon ring has efficiency to absorb the heavy metal ions such as the cadmium or nickel, cobalt, and chromium ions, the divalent and trivalent ions. And similarly, we also tried for organic contaminants like the dye methylene blue. So methylene blue is a common dye that is used in the dyeing industries. All the textile industries know. They use this methylene blue, okay, because that is one of the key dyeing agent. If you visit to Tirupur, okay, you will know uh, the water will be very colorish. The sewage water or the water that flows in the rivers and all, it will be very colorful. Why is because the dyeing industries use different types of dyes, and they actually release the untreated effluents or effluents into the local water streams. So we have different types of dyes. We have thousands of dyes, in fact. Okay. So methylene blue, brilliant green, crystal violet, and rhodamine beads. These are a few common dyes, organic dyes, that are used by industries. So what we have done is we have tried to understand how the watermelon ring can be efficient in controlling the dyes, in fact, like organic, removing the color or converting the color water into colorless water. So because methylene blue, it's a blue, when we add this particular dye, the water turns into bluish color. So we have tried to convert the blue color water into colorless water. So which means that the color of the water just due to methylene blue. If it gets converted into colorless, then we can understand that the water is free from methylene blue. Okay. So we have carried out these investigations, and the first, if you see, the removal of nickel and cobalt with the help of watermelon ring. This particular research was published in the International Journal of Mineral Processing. Okay. So in the year 2013. So that was our first publication, in fact. So we have successfully published how watermelon ring can effectively absorb nickel and cobalt ions from aqueous solution. And secondly, the methylene blue adsorption, like how the methylene blue can be effectively absorbed by the native watermelon rim. Native means untreated watermelon rim. Okay. So we have investigated how methylene blue can be removed in batch and continuous process, and we have published this particular research in the desalination water treatment in 2015. Then comes the modification. So now we understood the surface characteristics of the adsorbent drive. So once we understand how the surface looks like, then we can able to improvise the properties of the material. So sometimes there could be some drawbacks in the material, so we can able to improvise that. So not to improvise or not to change the surface of the watermelon. So we have considered a modification of the surface of the watermelon rim. So we have adopted two steps. One is protonation and second one is activation. Protonation is nothing but removal of the alkali metals. Like if you see earlier, I showed you this energy dispersive X-ray analysis, right? So there we could see potassium and magnesium ions present in the surface of the watermelon powder. So when we protonate it, what happens is we can able to remove the alkali metals that are present on the surface. Okay. So the protonation step is very simple. We have taken the watermelon powder and we have considered a 0.1 molar HCl solution, and we have dipped the powder, or we have soaked the powder in 0.1 ml HCl solution for 1 hour. Now during this process, what happens is the acid will get exchanged, means the H plus ions that are present in the acid solution will replace the potassium and the magnesium ions. So as a result, what happens is all the potassium and magnesium ions that are present on the surface will come into the solution. And in the place of potassium and magnesium, the H plus ions will go and bind onto the surface. So we are just trying to eliminate the alkali metal ions so that the efficiency of the material can increase, like more number of adsorption sites. Adsorption sites in the sense the adsorbate molecules like the pollutants, cadmium or nickel or cobalt or even methyl blue or crystal violet. So they can come and contact with the surface, right? So when the surface is occupied with the potassium or magnesium ions, now the surface is not free because already there is a ions that are existing. So if you're able to remove that and if you're able to replace with the H plus, no, now the H plus can easily get exchanged with the pollutants when we can able to change the pH. With the help of pH, no, just by altering the pH, we can able to make the pollutants to bind onto the surface in the place of H plus ions. Okay? So that is always possible. Okay? So because of that, no, we have considered the protonation step and we have successfully protonated it. And on the other hand, if you see on the right hand side, we have activated watermelon rim. So this is not activated charcoal, this is activated watermelon rim. Okay. Again, this is a very simple step. We have taken orthophosphoric acid, so 1:1 ratio. Say for example, 1 gram of watermelon rim and similarly 1 gram of orthophosphoric acid. Okay. So we have taken that and we have mixed it and then we have just kept it in an oven and heated it at 105 degrees Celsius for 2 hours of time. Okay. Now during this heating process, what happens is the acid will actually interact with the surface of the molecules, the adsorbent. So as a result, it's going to char. It's going to convert the molecules into a charring one. So charring takes place in case of this contact. So orthophosphoric acid is going to convert the natural watermelon into a charred one. So that's what we call it as an activation process. So modification was done in 2 steps. Am I audible? Can you just confirm whether I'm audible?
Yes, sir, it's audible.
Yeah, thank you. Because that's a power shutdown, so I thought whether Wi-Fi is working or not. Yeah, thank you. Okay, so now just to confirm whether the modifications what we have done was successful or not. So we have considered again the EDX patterns. Okay. So the first one is for the protonated step. Okay. So now if you see after protonation, when the material was contacted with the HCl, okay, now you can see there is no potassium peak here. Earlier there was potassium peak, right? There is no potassium and there is no magnesium, and we can see only chlorine. So even we have used HCl, right? So that there could be some chlorine atoms, but no potassium and no magnesium. So this confirms that the surface is free from alkali metals. Okay. And similarly, when you go for this activated one, when we have contacted the orthophosphoric acid with the watermelon rim, okay, now we can say again there is no peaks for the potassium and magnesium, but instead you can see peak of phosphorus. Why is because orthophosphoric acid contains phosphorus, right? So the phosphorus remains in the material, the activated material. Okay. So this confirms that our target was achieved. Means what we have aimed, so we were able to achieve that. Okay. So we have published a couple of papers on that. Not even a couple of papers, even many papers were published, like the protonation one. So we have used the protonated water membrane, and we have tried to uh, convert the colored water into colorless water. So here, if you see in this study, we have considered three dyes, three basic cationic dyes, like the methylene blue, and then the crystal violet color, and then rhodamine B. It's a rosy colored sustainable energy journal. The next type of adsorbent which we are focusing on now is nano adsorbents. So nano adsorbents are quite popular and they are more efficient. Why? Is because when the adsorbents are nanoscale, that's 10 to the power minus 9 meters. Okay, so it means they are very small, and the effective surface area is very high. When the adsorbents are so small, the effective surface area is very high. So as a result of that, no, the efficiency also will be very high. So nowadays, no, nano finds its application in all domains. It's not just related to chemistry, even electrical, all the home appliances. If you see why the size of the home appliances are becoming very smaller and tiny, if you just take a TV. Earlier, we used to have CRT TVs, and the size of TVs are very big. Now we have wall-mountable TVs, and the cell phones. If you take cell phones now, they are becoming quite smaller, tiny, and slim, and the performance of the phones are increasing twice because of the nanotechnology and the nanomaterials. In fact, nanomaterials. So nanomaterial finds its applications in all parts, and even in adsorption also it has a role to play. So adsorbents which are in the nanoscale level are called as nano adsorbents, and we have many nanomaterials used as nano adsorbents, and variety of nano adsorbents are investigated. Like most of the nano adsorbents are like the metal sulfides and metal oxides, okay, so which are effectively used in water treatments. Okay. So even we have synthesized the zinc sulfide nanoparticles, okay, so which are in the nanoscale level. There's 5 nanometers. The particles were the size of 5 nanometers, and we have used this zinc sulfide nanoparticles in removing the methylene blue from the wastewater. So we have tested for converting the blue water into colorless water. So we have successfully achieved that, and that particular investigation or the findings was published in the Desalination Water Treatment Journal in 2018. And fixed bed columns. Now, if you see the earlier investigations, everything was done in the batch scale. It means we take some quantity of water and then we add a particular quantity of adsorbent. We just shake it for a particular time. Okay, we allow the adsorbent and the pollutants to come in contact with each other. So we allow for 60 minutes of time or 2 hours of time. Okay, and then we filter that, and then we take this solution for analysis. So that's what is done. That's what we call as a batch process. Okay. So in that case, we have a drawback like every time only particular quantity of water can be treated, and we have to wait for treating the other water that are produced from the industries. So we have time constraint there. So if you want to take that to any industrial application, then we need to study the fixed bed column studies. Fixed bed column is something, but it's a continuous process. So where we have a huge amount of adsorbent packed in a column, and we allow the pollutant loaded water continuously to pass through this column. So when the water passes through this column, continuously what happens is the pollutants are removed, and then the water that comes out of the exit of the column will be free from pollutants. So we need to study like to till what extent this particular column can continuously work, like for 1 hour or for 2 hours or for 1 day. So that will help us to design an industrial process or industrial column. So what we have done is we have made a smaller columns with the help of the burettes. Like we have burettes, right, which we use it in chemistry laboratory. Okay. So we take a smaller burettes, and then we fill the burette with the adsorbent, like the water membrane powder or the zeolites. Okay. So we just pack the columns with the materials, and we allow the solution to pass with the help of a pump. Okay, we have a pump which controls the flow rate. So here we have the, say for example, lead solution, and this pump now takes up a particular flow of particular quantity of the solution. Okay. And with the help of that, we are trying to allow the pollutants or the polluted water to come in contact with the surface of the adsorbent. Okay. So when the solution passes through this adsorbent, okay, now what happens is the adsorbent and the pollutants are going to interact, and adsorption is going to take place. And then finally, what happens is the solution that comes out of this column now will be free from lead ions. In this case, I have just indicated as lead. Okay. So it will be free from pollutants. So continuously, what happens is we can able to monitor. So we can collect the samples from the exit, and we can able to test it with the atomic absorption spectrophotometer. So which helps us to know the quantity of or the amount of the pollutants that are present in it. Okay. So we have done this analysis, and one of our investigation was published in the Environmental Science, Water Research and Technology Journal, which is published by the Royal Society of Chemistry. Okay. So any researcher now will be proud to publish a paper in Royal Society of Chemistry, which works from London. Okay. So our research was published in this journal. Okay. So that is the fixed bed column analysis for the removal of lead ions. Okay. So these are the few research activities which we have done and we are working on. Okay. So we work on different class of adsorbents, starting from the agro waste to the zeolites and the ionic liquids and the nano adsorbents. So we work on these 4 class of adsorbents, and even we are trying to work on the other adsorbents also. Okay. So these are the few findings which we have done till date, and which we have published in several journals. Okay. So now I'm done with the presentation, and now it's time for questions. So if you have any questions or queries, I'm open now. Yeah, any questions, any queries or any doubts if you have, or if you want to know much more about any topic which we have discussed. So I'm open, I'm ready to answer.
Sir?
Yes.
Sir, can you give me another natural products to be used for absorbance for removal of heavy metals?
Natural material, we can use any material. Like if you see here, we have considered watermelon ring, and there were investigations done for banana peels, orange peels, and even we can take this sugarcane waste or the rice waste is there, right? That we can use, and then the vegetable waste, even the onion waste is there, right? Even that we can use, or the peels of any vegetables can be used as an adsorbent, and polymers like cellulose materials can be used as an adsorbent, and the dead plant materials, the plant leaves and the plant flowers, stems, everything can be processed into a powder form, and that can be used as adsorbent, because all the materials contain organic molecules, and they have functional groups like hydroxyl or carbonyl or carbonic acid groups. So these groups have ability to interact with the heavy metal ions. Like for example, if you take hydroxide ion, OH, so it can give away the H plus ion. So the oxygen will be having the negative charge, and the heavy metals are positive. Say for example, lead is 2 plus, and it can bind to the oxygen because oxygen carries negative charge. So there is an electrostatic attraction between the negative and then positive ions. So that is how the process takes place. So we can use any natural material, and we can use any fruit waste materials. We can use any vegetable waste materials, and any dead plant materials, or even animal materials that can be used as an adsorbent. I hope I answered your question.
Thank you, sir. Thank you.
Sir, I have one doubt.
Yes.
Sir, if absorption process means you observe something means it show any reaction changes or not, sir?
Yeah, if you see again in adsorption, there are 2 types of adsorption process. One is physical adsorption, and second one is chemical adsorption. So physical adsorption means there will not be any reaction taking place between the adsorbent and the pollutant. So there is no any bond established. It is just due to the electrostatic attractions or weak van der Waals force of attraction. So it can be easily again removed from the surface. Means we can able to retain the adsorbed. But there is another type of adsorption which we call as a chemisorption. So there, the chemical reactions will take place between the surface and the pollutants. So in that case, there will be a chemical reaction, and then a bond establishment takes place. In this case, it is very difficult to remove the pollutants from the surface because there's a bond established. So it takes usually chemisoption takes place at a very high temperatures because we need this activation energy. So physical sorption can take place at room temperatures, but chemisoption takes place at very high temperatures. So chemisoption is also possible. Yes, chemical reactions can take place at the surface, but it all depends upon the nature of the adsorbent and adsorbate and the conditions. I hope I have answered your question, I guess.
Sir,
Yes.
so why we are using a zeolite as a absorption? If there is any absorption rather than zeolite?
Zeolite, if you see, it's a natural material. Sand is a natural material. It is available in a huge quantity. So we don't need to process that. We can straight away take the zeolite and use it as an adsorbent. So no treatment is required. But if you see in case of fruit peels, I have shown you the process, right? We have to wash it, we have to dry it, we have to powder it. So there's a methodology or there's a process to convert that into adsorbent. But zeolites are natural materials. They are naturally available. So straight away we can take that and we can use it. So that is the advantage of zeolites.
Finally, you can how much yield you can obtain this absorption, sir?
Yeah,
Yes, you can use it for the zeolite.
Yes, yes, yes. It all depends upon the conditions. So when we go for adsorption, we need to optimize the parameters. Parameters like the first thing is pH. We need to see at what pH we get the maximum adsorption, maximum yield. So the first thing is to optimize the pH, and then the contact time. So how much time we allow the pollutants and the adsorbent to come in contact. That's the second parameter. And the concentration. Concentration of the means how much quantity of adsorbent we add to that. If the pollutant concentration is very high and we add little amount of these zeolites or a solid adsorbent, then we'll not achieve 100% adsorption rate. So we need to optimize the conditions. So the first thing is pH. So pH determines the adsorption efficiency.
Okay, sir. Thank you, sir. In MPhil, I'm also doing the project in adsorption, sir.
Oh, that's great.
So I was doing the charcoal in the seeds. It is used for the charcoal.
Okay, okay.
So, and in various concentration, I can do it the project. It will be increasing the yield. Yield it is a more increase.
Yes, removal efficiency.
That's why I'm asking the question for. That's why I'm asking the question for what is the zeolite it is using.
Yeah, we have different types of zeolites. Like a few are sodium based zeolites and a few are aluminosilicate. The composition might vary, but all zeolites will be helpful in removing the pollutants. But we need to optimize the conditions, as I said, the pH and the contact time.
Oh, okay, sir. Thank you, sir.
Any other questions?
Yes, sir.
Yes.
What are the best absorbent for the treatment of used motor oil besides clay?
Come again. What are the
Best absorbent for the treatment of used motor oils besides clay?
Yeah, activated carbon will be one good choice. I would suggest activated carbon beside clay, because active carbon was the one that was used initially, but because of the cost, we have kept that aside and we were trying to identify other adsorbents. But I would suggest activated carbon as one of the potential adsorbent, because it has proven its ability to adsorb anything. Even it could be an oil or it could be organic pollutants or inorganic pollutants, whatever it is. I would suggest activated carbon.
Okay, sir. Thank you.
If there is any questions, then I think I'm happy to end this session. So thank you. So here are my contacts. So if you have any queries or doubt, you can call me or you can just email me. So I'll be happy to answer or clear your queries or doubts. So thanks for the opportunity for inviting me to deliver the talk on the national webinar. Any
Thanksgiving are one giving aspect of humankind that attributes a lot to deserve away. I deem it pleasure to invite you Miss A. Soumya Agnes, third chemistry, to deliver the vote of thanks.
With grateful heart, I thank the Almighty God who pours His blessing upon us for this most amazing day. I thank our management for support and guide us to make a webinar as a grand success. Also, I coordinately thank our chief guest, Dr. R. Lakshmipati, by inspiring us through his valuable presentation and for his dynamic speech on the role of absorbment. Last but not least, a special thank to our head of the department, organizing president, all staff members, and lovable students who have been source of strength to us through their support and various other kind of help. Once again, thank you all. Thank you,
Thank you,
sir.
sir. Thank you. Thank you to all. Thank you. Those who are participating in this webinar, thank you. Dear participants, kindly all of you fill the feedback form.